So this morning we've heard a lot about sort of the high-level goals of information exchange, the complexity, sort of the policies, how all these things are going around. And my talk today or this afternoon is a little bit more about kind of like the plumbing. I mean, okay, so once you have all these policies and all these things and make the decision that you actually want to share something with somebody, how do you actually get that done and how do you actually enforce those policies, which come down to security, cryptographic techniques, wire-level communications, data formats, and so on. So how many people here have heard of DDS, Data Distribution Service? Okay, about half the people. How many people think that they've used or have been on some system that uses DDS, Data Distribution Service? About a third of the room. I think by the end of the presentation, I hope you will all realize that you all have actually used systems, and probably will use within the next couple of days systems that use data distribution service. So what I want to do is sort of organize my presentation into 3 topic areas. First of all, understand what are the challenges and goals of connectivity, because there's a lot of connectivity technologies out there you probably are aware of, and then how do they all fit together, right? And why did we take the time to develop all these specifics at the ONG? Second of all, kind of give you a little bit more detail on what is DDS, how is it different from those other connectivity technologies you may have heard or not about. And then some kind of brief overview of DDS applications, and then I'll cover security aspects in the last part of the presentation, just so you understand how this fits with the presentations that we've seen this morning of information exchange and so on. So first of all, I think we're all kind of well aware of the hype around IoT, right? Internet of Things. Now, you can think of 2 aspects of IoT. When people think about IoT, most of the time, people think about what we call the consumer aspect of the IoT, kind of like the health devices, health bands, phones, your sort of your devices at home that automatically control your fridge, your lights, all these type of things, right? Now, that's kind of 80% of the hype, I would say. Most people think about that when they think about IoT, but really, most of the value of IoT is going to come in the industrial side of IoT, the industrial applications. How is it going to help transportation, energy generation and distribution? How is it going to help healthcare and so forth? And that's what I'm going to be covering a little bit on my presentation today. Now, in the context of IoT, an OMG program that is called the Industrial Internet of Things that has been mentioned in the last couple of days is a very important force there. So this Industrial Internet of Things is probably the largest sort of worldwide organization of companies trying to work on defining sort of architectures, standard references, and technologies that are relevant to help this industrial sort of revolution using internet technologies. So this organization is called the AIC, the Industrial Internet Consortium, and this organization is kind of address the problem of connectivity, try to think about how to really leverage these internet technologies in the industrial world. And what they've done is basically come up with what's called a reference kind of a stack for connectivity in industrial systems that kind of layers the different levels at which information exchange occurs, right? You can start from the low level when we're talking about things like, well, Wi-Fi or hardwired Ethernet, time-sensitive networks, 5G that is coming, right? And as you go up, you go into the sort of more classic internet technologies like the network layer, like TCP/IP or UDP/IP, right? But as you go up there and you are trying to actually communicate, information, you have to go and come up with higher level concepts, like the concept of data. How is the data structured? What are the attributes of the data, right? What are the exchange patterns? Is it a publish-subscribe? Is it a service-oriented architecture? So that's what's handled at the framework level, right? And then on top of that, you've got an information model that kind of describes the semantics of the data. So that's kind of like the modern view. I mean, in the old days, there was something called the 7-layer OSI reference architecture. And then it became kind of the 4-level kind of internet sort of architecture. And now this is kind of, you can think of that, of the 6-level sort of industrial internet architecture that kind of captures essentially the layers of software that you actually buy today or you use today. So when you go at the practical level and you say, okay, how are people actually building these systems, you can see how the different technologies you've heard about kind of fit into those levels, right? So like I said, the bottom level are the things that happen more at the hardware level, which there is a lot of innovation going on there with 5G, time-sensitive networks for real-time sort of Ethernet. And then you've got the middle layer that is kind of like very well established now with TCP/IP, UDP/IP, HTTP. And then you've got kind of like the framework layer where it's actually where all the communication patterns occur, publish, subscribe, service-oriented architecture, where there is a lot of innovation as well occurring, right? And there you have things like DDS, which is the technology I'm talking about, but other things like MQTT or web services or OPC that are kind of predominant in different sectors of industrial type of applications. And of course, if you go to like consumer type of applications, you've got also a lot of other technologies sort of in big data and things like that that fit on that architecture, right, on that same framework layer. So you would think that really most of the innovation, and that's why this is kind of an hour-shaped glass, is because it's trying to express the fact that a lot of innovation is happening at the bottom. The center with TCP/IP, UDP/IP, internet is basically kind of established, and everybody's kind of fitting there because there is so much install base on the worldwide, right? But at the top, there is again a lot of innovation because the richness of information exchange, quality of service, patterns, and so forth demand that kind of richness in the technologies deployed. And then on top of that, the different applications would be deployed using that infrastructure. So the point being made here is that DDS is actually in this reference architecture published by the AIC, they actually identified just 4 as the kind of recommended or predominantly used in industry technologies for using connectivity. And they come up with like a sort of a chart where they describe kind of what is their sweet spot, what are the best used for, how do they meet the functional and non-functional requirements of control systems or industrial systems in general, about scalability or about being able to have standards-based, multiple vendors interoperability, security, availability in different programming languages, in different operating system environments, so you can go from embedded to cloud, those types of things. Don't want to spend a lot of detail reading through that. You have the slides later to look at, but basically it's a very thorough paper out there that you can get from the IIC that kind of gives you like a landscape of connectivity, everything you ever wanted to know and more about connectivity and where it's going. So that's sort of the context for why DDS is an important technology, right? Because it's a widely utilized technology in the context of industrial use of internet technology. Basically, the next revolution, they call it a 4th industrial revolution, after electrification and steam and so forth, is now coming sort of the use of internet technologies to revolutionize the way the industry works. So in a very simplified view, when you're using this type of connectivity technologies, you are now removing yourself from writing, TCP/IP or networking packets. You are now talking to some kind of middleware layer that takes care of higher level abstractions like publish, subscribe, request response, service-oriented invocations. And then your application can sit there and talk about what data it wants to send, what are the quality of services, reliability, durability, persistency, timeliness requirements for the different flows of data, and then somehow this middleware takes care of that. So, so why is DDS sort of a good fit for this? It's sort of, you can think of it as a 4th generation architecture. We started in the early days when the internet came out with technologies that were very much at the same level of the technology that the internet provided, which was like point-to-point connection. So you have a point-to-point connection where you can send data, and then all of a sudden people said, okay, we're going to put a file transfer protocol like FTP. That is kind of like the same thing. You connect to one place, but now we have a little bit more like with some commands to read, write files, and so forth. Or we're going to have a mail system, an email system where you actually connect to the mail server and send data, right? But those are still point-to-point technologies. Then people are starting saying, well, it's very hard to handle all these point-to-point connections. You really want to talk about a higher level abstraction, what kind of information I want to distribute, what kind of service do I want, right? I want to read a file. I don't care whether you have the file or he has the file. So I want a higher level sort of separation. And you end up having a lot of kind of broker type systems where it's kind of like a database. You request your information from the database, and the database has everything, and you get the response back, right? And that takes care of delegating to whoever the pieces are, which is a nice abstraction, but it's centralized, and it sort of doesn't scale very well. Kind of like a choke point, like everybody tries to go through the same intersection, and you get a big traffic jam there, right? And then in the industrial world, people started saying, well, we need kind of a much more parallel architecture where all the traffic can go, all the lanes can go in traffic. And there have been several iterations of that. And finally, I think kind of like the data bus technology, which is what DDS does, kind of puts together the concept of a centralized way to think about the information, while at the same time you have a distributed access peer-to-peer to the data. So it's kind of like you want the best of both worlds. You want to be able to think of it as if it was central, right? Don't have to address the individual endpoints, but at the same time not have to go to the center to get the data directly from the source. So that's why it's kind of like a fourth generation technology. And the advantage of using this type of technology is that a lot of things that the application normally would have to do, worry about what is the information, how to format the information, how to know the availability, keep track of the connectivity, what happens if I become disconnected, did the last message I sent get received, did it not get received, all those kinds of things that increase a lot of the application logic and complexity get done inside the middleware layer, so the application can now operate at a much higher level, right, about what does it want to receive, what does it want to send, what services it wants. This is a very high level kind of what DDS is for. And then when you go to an industrial type application or a transportation type application, what ends up happening is that you're kind of organizing that information into some kind of scopes or layers, because even though kind of it's a global information space, it doesn't make sense for somebody inside a work cell to be looking at information in a different work cell in a different factory that has nothing to do with the business that they're trying to do, like manufacture a piece of equipment, right? So it has a lot of locality. You want to be able to see the information that's near to you, that's relevant to you. But at the same time, there are systems that need to sort of monitor what's happening at all the different locations and integrate all that, right? So it's kind of like a layer, like, it mirrors what any organization have, right? So organizations are also hierarchical. You are working within a group. You have a lot of information exchange with the team members in your group, but there is also group-to-group communication and department-to-department communication and company-to-company communication, right? So there are layers of communication. So something that I can be doing in my group, that I exchange a piece of information with somebody in my same work group, that same piece of information can end up in a different company because it's relevant, right? So I make a decision, that decision gets kind of translated at the next layer and gets reflected into something on the next layer, and finally becomes a piece of, a contract, some document, or something that gets exchanged with some other company, right? So you can see how information is flowing both sort of laterally, horizontally, and vertically, right? And that's sort of what this kind of architecture allows you to do. It allows very high sort of decisions within kind of an area that is closely connected, sort of real-time decisions, autonomy decisions, but also there is ways to sort of bridge between one layer and another layer so that some of that information that is happening in one place can be reflected in a different place. And I have some better examples when I talk about the applications, so you can see that how fits actually specific domains. So these are sort of, in terms of how DDS is used, we use the word IIoT for Industrial Internet of Things to differentiate that from the sort of consumer IoT. And sort of the main sort of segments of the Industrial Internet of Things are healthcare, transportation, communications, energy, industrial sort of manufacturing, I would just say more than industrial, and then defense, right? And these are sort of typical applications in those domains. And there are actual pictures from actual systems that are actually using DDS as the underlying technology. And then you also have a lot of, so DDS is, as we will see, a standard from the OMG, but then there are other standards that depend on standards, right? Because in the end, the standards layer on top of standards. Like DDS uses IP and TCP, which are internet technologies, and the internet technologies themselves use Ethernet, which are IEEE standards, right? Or IETF standards. So likewise, there are other standards in other organizations that are building things that depend on DDS as the underlying technology, and they're building information models, information exchange patterns, right? Like the IEF that we heard about this morning in the presentation that talks about the information exchange uses DDS underneath to actually realize some of those information exchanges, right? So these are example organizations that are building specifications that use DDS as the underlying technology. Like, for example, NGVA stands for the NATO General Vehicle Architecture. It's a standard that came out kind of negotiated between the different NATO countries on how to organize all the information inside military vehicles like jeeps and things like that. In the old days, or even in the current days, every system that you bought comes with its own display, its own sensor, and you can take a picture of this thing and find that the driver has 5 different screens because each subsystem, like this radar has its own display, and this gun has its own display, and this thing has its own display, right? Because they're not communicating horizontally. It increases the complexity. So they sit down and they say, how are we going to get everybody to use a common information model? They create a standard, right, like NGVA, and they say, well, that information exchange has to use some technology. What technology is that going to be used? So they say, well, we're going to build our standard on top of DDS as the standard that actually carries the information around. And that's just one example. We've got things like Eurocontrol that handles traffic management system for Europe. It's also built on top of DDS. Things about power distribution. OpenFog has to do with fog or edge-based computing. So phase is another standard in avionics. So it's a lot of all these other systems that are kind of depending on this kind of technology. So this is an example of how this whole thing's together in a real system that is actually running the Grand Coulee Dam, which is like the largest energy generator in the US. It has about 7 gigawatts of power. So anybody who's in the East Coast of the US is actually using DDS because their power is supported by the Grand Coulee Dam. Like the Grand Coulee Dam that stops working, there is not enough energy generation in the Western United States to power the grid, basically. This thing balances the grid. So they have, we talked about those layers. So this thing actually has like 7 power stations, like 7 turbines, but seven things that are generating the power, right? Each one of those has like a segment bus, right, where they are controlling the actual device, monitoring that is the operating conditions, turning on different things. So they are communicating fast within a bus, right? And there is 7 of these things. These things are themselves integrated in a control room bus, which is then integrated into a monitoring bus and so forth. So some of the information is flowing horizontally, and some of the information is flowing vertically, right? And of course, in between these, there is firewalls and all kinds of things, right? Another example is autonomous vehicle. That's another area where DDS is being quite broadly used because of the whole push for autonomy that brings a lot of demands for high-speed information exchange. Now you've got LiDARs, you've got 7 cameras, you've got radars. All this information is flowing in real time. It has to be analyzed. You have to derive a picture of what's going on, and you have to make a decision of, do I keep going? Do I slow down? Do I have to turn? So how all these things happening? Well, you've got essentially a bus that sort of integrates all the information that is inside the vehicle, where all the pieces can be looking at the same information at the same time to make their own decisions, right? And they're coming with planning, awareness, data fusion, and so forth. Now, that vehicle, in the end, also has some information that communicates with the infrastructure, right? Because the information about where is the vehicle going, what's the health of the vehicle, those things are of interest to people trying to figure out where the vehicle is doing okay. Has there been an accident? And now if a vehicle has an accident in the modern vehicles, it will automatically notify the manufacturer or some alarm system, and you'll get immediate assistance, right? Say, hey, we've detected that you've had an impact. Are you okay, right? You hear that in the thing. So there is information from inside the vehicle that is actually being propagated in real time outside. So that's where the layers come, right? You've got horizontal things going inside, and then things that are going outside. They're talking about having vehicle-to-vehicle communication, like as you're approaching an intersection, and you don't have visibility, but there's a vehicle around the corner, it can be broadcasting on the kind of neighborhood network its intent and its location, so you know it's happening. So even if you don't see, your vehicle knows it's there, so it's going to slow down. And the same thing happens with maybe like a pedestrian or bicycle, right? You could have cameras that are monitoring the bicycles and are notifying the vehicle, hey, there is a bicycle approaching here, so you immediately don't hit them into the intersection, right? So it's a lot of locality. This information is relevant based on the fact that you are close to this other system that is actually having an intent that intersects with your intent, right? So the idea of having that type of awareness on the information flow is very important. And this is another example from clinical decision systems. I don't know how many people are aware, but sort of medical errors are considered sort of like the 6th leading cause of death in the United States, behind maybe even higher than the 6th, like behind cancer and heart condition and so forth. And the reason is that even though there is a lot of systems monitoring the health of the patients, these systems are not integrated, right? So you may have 5 different devices, one monitoring your heart rate or monitoring your breathing rate, your oxygen saturation, but they're not talking to each other, they're not being integrated into a single sort of system that looks at all these things and says, hey, there's a problem here, let's take care of this patient. So as a result of these systems being independent, each one of them is firing its own alarms whenever they detect something. But the problem is that they are quite fragile. Like a lot of things can cause an alarm, right? If you have some kind of like heart rate monitoring and the person that has the device there kind of grabs onto the handle with the same hand, all of a sudden that will show us a disruption, right? And if something else is happening, so it's very easy to get each one of those sensors to detect an anomaly, right? So as soon as they detect an anomaly, they fire. And then the end result is that you've got all these sensors constantly firing. So it's kind of like the alarm, right? You keep that we hear. You hear it every 5 minutes, you hear it again, and there's like, okay, I'm not paying attention of it anymore because I know, that I already seen it. So you're kind of missing that one important situation where there was a real alarm because there was so much noise of false alarms around that. So in order to sort of eliminate that situation, what you need is sort of to integrate all those sensors so you can have sort of intelligence and say, if I see this and I see that and I see that, now I know it's a real problem. If I see only this, then I know that this by itself, it couldn't be a problem, right? Because this one metric alone doesn't indicate that there is a serious situation. So what you need is to basically to be able to integrate all those sensors into a common information model, real-time information exchange, so you can develop applications that are monitoring that. So at the high level, it's very much the same as the traffic driving situation, right? You have to do a sensor fusion, bring into a common bus, have analytics that in real time look at that and make a decision. And that, you can think of that, well, this is kind of like, almost like a patient-oriented. You can think of this thing about each one patient, all the things that are relevant to that person connected to them, and the analytics that are looking at what that patient is doing, is a little kind of bus. But now, if there is an alarm, that needs to be communicated somewhere else. Could be in a different room where the nursing stations are, which are monitoring these things that says, there is somebody here that needs some attention, right? So that's where you get, again, a horizontal communication and a vertical communication. And then, of course, there is things that are going just less real time where long-term, this data is recorded, so the hospital can keep a record of what were sort of like the conditions that the patient went through, log their health metrics and so forth. It could be a store, it could go into the record of the patient. So you go up those layers, starts becoming less real time, right? It's not so critical to record that data in 10 milliseconds. It could wait 1 minute or 2 minutes, right? And so forth. And then the patient goes to a different hospital. Now you need to transfer those records there. So you can see that there is a layer there that where some information eventually can be going to a very broad location, new patient. In fact, this type of architecture is even being deployed now for emergency response. Like as the ambulance goes to an emergency situation and takes on a patient, they start administering care, right? And as the patient drives to the hospital, they need to know, what has been done to this patient. If they administered some drugs already, they don't want to be administering something that's incompatible with that or overdosing the patient, right? So there has to be real-time information flow as opposed to what they do now, like write something in some sheet that gets misplaced, doesn't get handed to the right person. This is the kind of medical errors that we were talking about earlier. There is just too many opportunities to do something wrong. So why DDS, right? So this is the need. We've seen that there is all this need to do all these different things. So what does DDS provide in the context of this type of applications? So earlier we said there were like a set of OMG specifications. So DDS is actually, I can't count anymore, but we used to say 7. It's probably more than 7 now. Everything that is above this red line over here are different DDS specifications, right? So we have specifications about the information model, the API, security, how to do service invocation, how to do publish subscribe, and we have also specifications on how to interoperate with other technologies like web type technologies or OPC UA manufacturing type technologies. And at the OMG, we basically work together with anybody that's interested in this type of technologies to kind of evolve the specification, create new complementary specifications. So we started this in 2004, and this, you can see, in blue is kind of the first release of each one of the specifications that we had, and then in black you have some of the key revisions of the specifications. So we kind of, every year we kind of have a revision of some of the specifications, new things get added. We have an active community of implementers. We have about 7 or 8 independent implementations, some on the open source, some commercial products. So it's a very vibrant type of group and technology base. So, so when all is said and done, you as a user, what do you get? Well, you get this kind of SDK that allows you to build applications. And you are a user, here is like somebody trying to build kind of an integrated sort of grid type of application. So they've got systems out there and devices that are trying to, they have information about what they are doing. They're generating power. They have phase. They are metering power. You've got other systems that are trying to monitor, make decisions. How do all these things communicate, right? So they create sort of a shared information model where they organize everything around concepts like domains, topics, structured data within those topics, keyed, sort of kind of like a database. You have every record, every item of information has a unique address. So you can then update and say, hey, I'm the same device. Before I told you I was rotating at 37 RPM, and now I'm rotating at 97, so please replace the previous value. So you can think of that and say, oh, that looks very centralized, and that's what I said earlier, right? So from your point of view, it looks like it's all central, right? It's very simple to think about it. But in practice, it is not centralized because it wouldn't be high performance. You wouldn't be able to communicate within, the devices in the patient wouldn't be able to communicate with the device that is just next to it or the thing that's monitoring in the same room if I had to go to a cloud and then come back, right? Or the car couldn't be communicating to the bicycle that is driving around the corner if all the cars in the world were all sending their messages to the cloud, and then the cloud was saying, oh, I guess you're in the same area as you. I better send you this information, right? That wouldn't be fast enough, and that wouldn't be robust enough. So this model of centralization gets then realized in a very kind of efficient peer-to-peer mechanism. And then we've got other capabilities to define quality of service. We can define all kinds of exotic things about how periodic the information is, how reliable it should be, what are the bounded latencies, sort of things that are important to sort of real-time or industrial type systems, right? It's not just about getting the data, it's also about how fresh is the data, which data is more important, those types of things, right? And then, like I said before, get it there fast enough because we're talking about real-time mission-critical systems, so they need to make the decision in time, right? So there is a lot of kind of, again, exotic and low-level capabilities built into this technology. But I'm just putting those just to sort of express the idea that, there's a lot of technologies that at the high level, they are trying to do the same thing. When it comes down to the details, depends on how they are trying to be deployed, what type of applications are going to need it, because the decisions that you make is like a car, you could have like a SUV, or you could have a Lamborghini, and they are both trying to get you from A to B, and they both have an accelerator and a brake, but one is about cargo and being robust to all road conditions, and the other one is about speed, so you wouldn't be able to use them for the same type of application, right? So the same thing happens with middleware. Another thing that's very important when you're integrating systems is to be able to really model your data. And DDS uses a standard called IDL, which is part of the OMG set of standards away, that has been also been revised and updated to add a lot of things that are important to the system. So you, for example, can annotate your data with information like what is the valid range of data, what are the units of that data, right? Which are things that are going to prevent errors, like somebody is like publishing a speed in meters per second, or kilometers per hour, and somebody's expecting miles per hour, and then they make a wrong decision. Because of that incompatibility, it has happened actually. And like there was a famous rocket that crashed because one part of the system was thinking as feet, and the part of the system was thinking it was meters, and then they made the wrong decision, and it kind of didn't take off properly. So those types of things are important in systems, so DDS also supports that kind of capability. Okay, so now with that context, what are some of applications? So like I mentioned, applications come in different domains, and of the 5 domains, actually DDS is deployed in all those 5 domains. So here are some systems I'll go, but in energy, it's pretty key for us in general, for the DDS community. Defense was actually the first big user of DDS, so it's actually deployed in most kind of defense systems out there, like both maritime as well as air. Then healthcare is also a big, you could guess by the examples I was giving, it's also a big user of DDS, and some of those companies are deploying DDS in their systems. This is an example of the hospital. You can see what big of a mess it is just to have one patient, right? All these instruments right now are not integrated. Any one of them can raise an alarm, right? You can imagine how many alarms are coming out of this system. It would be impossible with having some intelligence there, right, to make the decision. And in fact, they're not even using the same protocol, so it would be impossible today to actually integrate them all without a lot of custom code, right? So this kind of standards is helping people build better solutions in that. And then transportation, especially with kind of like the new autonomies trying to make things more autonomous, less human involvement, you need more real-time decision making, and that's also another place that's in a lot of DDS applications. So I want to remark this because we're in Canada, right? So, and this is the Canadian Air Traffic Control System. So the Canadian Air Traffic Control System is now using DDS as the way to communicate their flight plans and make their flight decisions between the different control centers in Canada. It turns out that the Canadian control system is like the second largest in the world in terms of like airspace coverage. I think it's only second to Russia. And they cover not just Canada, basically, that whole there, but they also cover all the North Atlantic routes. So you're flying from Europe to the US, you are going through Canadian Air Traffic Control System while you are in flight in the North Atlantic. So how many people have flown or are planning to fly in the last 2 weeks over some Canadian Air Traffic Control space? Okay. Everybody else is local? But you may have flown in the past, right? So you've taken sort of any flights in the North Atlantic or in Canada, you've been a user of DDS. So this is why I said at the very beginning that you probably don't know it, but you're already a user of DDS in some form, without going to the hospital or having an autonomous vehicle, right? So, but it's not just that. I mean, a lot of the new energy generators putting out there, this is like, used to, I'm not sure if it still is, the largest wind power generation in the world of the coast of Denmark, about 500 turbines, each one 100 meters, which means it's bigger than a 747, right? Each one of those wind turbines. And again, it's very complex. When I was made aware of this system and realized what they needed to do and how they architected, realized the complexity of this. Each one of these devices has hundreds of variables being monitored in real time to make sure this turbine doesn't break, right? Because there is wind gusts, there is the angle of the blade, there is the speed of the blade, the phase of the energy that you're generating. If this thing breaks, it's actually pretty expensive to repair one of those things. In fact, the way they service these things is they land a helicopter right there on the hub. That's so big, right, on the hub that they can land a helicopter, and that's actually the cheapest way to get to one of those things. And then you can realize, well, it's not going to be easy to put one of those blades if it breaks down. So in fact, what they do is they monitor the health, and if they see something is not going well, they'll kind of degrade the operation. They'll say, okay, well, you're not going to be producing so much power. You're going to be backing off on the aggressiveness of your blades so that when there is big wind, you are not spinning so fast. So we'll much rather take a 50% degradation of your power generation, but continue your lifespan for the 30 years or 50 years we expected you to be there, rather than having to service you earlier because it's very expensive to go and try to service one of these things. Grand Coulee Dam I already mentioned before, so that's live since 4 years now. So again, we haven't had any, to my knowledge, I live in California, so we didn't have any blackouts, so I think our system is working there. Audi is a big user as well of this. They first became aware of it trying to solve the problem they had trying to do testing of their in-vehicle systems. They had a lot of components from different manufacturers they had to integrate, and then they realized, okay, we can also use it for our vehicles. So they're kind of in the next generation now trying to use this in their vehicles themselves. I mentioned the Navy and the aerospace and defense. Most of the NATO Navy systems deploy something called Aegis. It's a combat management system. And that is a sort of thing that integrates the radars and the weapons and the situation awareness and tells you, okay, here is some bad things that you need to worry about, and here's some other things that you don't need to worry about, and takes action. All those things are integrated on top of using DDS as the kind of backbone for that communication. And that's been around for quite a while, like I think over 10 years now. They're going through the next phase now, and they're including the security features that we just added to the DDS security specifications. So as they renew their system, they're taking advantage of new revisions of the specifications. Transportation, this is train transportations. And then finally, I just want to talk a little bit about security because it's so essential, right? A system that is not secure these days cannot be in the internet. Let's just face it, it attracts like a honeypot. People that are either just trying to have fun or they're just plain, malicious, trying to really cause some damage, right? And the more important and more critical the system, the more attractive it becomes to all these hostile operators there. So now, again, security is a very complex subject, and there is many ways to do a secure system. And in fact, you kind of have to employ all the different ways, because one of the kind of tenets of security is about defense in depth. It's like you have to have different layers of defense. It's like the old castle, you've got the moat around it, and then if people cross the moat, then you've got the walls. But if they cross the walls, you have a second layer of walls, and then you have the final thing, right? Because you kind of have to make it more and more resilient. And if you have a very broad border, it's very hard to secure. But you need to kind of filter out 90% of the events there, so then you can take care of the remaining 10% at the next layer, and so on. So DDS security layers on top of all the other security mechanisms that you may already be using, like perimeter defense. Right? You need to firewalls. You need to have, you need to have encrypted LANs. All these types of things. Your operating system needs to be secured. You need to have your virus detection, your intrusion detection. All these different systems have to be there. But after you got all these things, you still need to secure the data, right? Because you cannot say, well, now I've protected everything, and now that I've protected, I don't need to protect myself. It's like saying, well, now that I'm inside the castle, we don't need to carry any weapons because no bad guys can get inside the castle. But the problem with that is if some bad guy gets inside the castle and you have no weapons, now you are lost, right? So this DDS security essentially brings security to the data layer itself. It's like now, yes, hopefully you don't get there, but if somebody gets inside and is able to inject packets on your network or observe packets on your network, it's still not able to tamper with your system because the data that is being published and consumed is cryptographically protected, and there is authentication of every entity that produces or consumes data on the network, and those entities have to show the right credentials, and then only then they will be given access to the cryptographic material that they need to produce or consume data, right? So that's kind of what the DDS security does. Here is an example from how this thing was used. Duke is an energy sort of utility in the US, and they had basically a problem, right? They have a problem that in their current system, they've got all these different devices, and they are built by different manufacturers, and they have their own connectivities and their own protocols. Some of them secure, some of them not secure. And before it's like, well, this whole thing is isolated, so maybe we won't worry about it. Internet comes, people are doing remote metering, remote this, remote that. All these connections are appearing to the network, and all of a sudden it's like, oh my God, what is the data? Who secures it? How do we take care of that? It's just too complicated, too many flows. So their new architecture has created what they call the open field message bus, a single sort of integrated way to exchange all the information. Now that open field message bus is built on top of DDS as the infrastructure, and they add sort of their own information model, data models, access control policies, and so forth. So by doing that, what they get is sort of that, going back to the presentations early this morning, you have a way to essentially create a single set of policies that then you can apply, and you can get a handle of what all the information is. And then you can have a common way to make sure that all the information that flows into this bus is being protected cryptographically, and who has access to the keys, and you have a single source of authority to decide to grant permissions, and so on and so forth. Now, always when you're doing security, it always starts with a kind of an analysis of what your threats is, right? What are the things that you're concerned about, and what are the consequences of those attacks, and then you have to deploy a solution to that, because security comes at some expense, both in terms of kind of CPU and memory and so forth required to do all these cryptographic things, but also, and perhaps more significantly, all the associated policies and complexities that have to do with deciding who has access to and then granting that access, right? So if you're going to be able to have, generally in security, in the human, you're going to have an ID system, and you have to have people biometrics and all these different things that identify yourself, but you're going to have some authority that measures all these things and gives them to you and so forth. It's the same thing in computer systems, right? If you're going to have some kind of certificate that identifies your application as being a valid application, a certificate is not valid without somebody that signs the certificate, right? So who signs that certificate? So I have to have, somebody there sign my certificate, and then you have to recognize that person. So we need to have some kind of process and procedure, so we all agree on who's the right certificate authority, and then that person needs to have process and procedures to make sure it only signs the right certificates and not the wrong certificates. So all these things that are built around, not the technical stuff of encrypting stuff, that's kind of almost the easy part. The hard part is how do you actually make sure that now you're not letting anybody create certificates or so forth. So, but of course, the technical stuff then is also important, right? So, because now that you've gotten all these great policies, if you don't enforce those policies, again, it doesn't help, right? So I think it's kind of a collaboration between the high-level perspective and the low-level perspective of actually making that work. So, when Duke Energy was looking at this, it's like, hey, we've got an ideal world. We think this is like that. But in reality, what we discover is that our network is much messier, and we actually have a lot of potential intrusions and potential agents that are not people that we expected. Like, they're concerned about fake devices, people that put fake meters that produce wrong data, fake things that pretend to be telling energy systems to produce more or produce less, right? The people eavesdropping in their network. So all these types of things they have to worry about, right? And this is not just for utilities, obviously, that is really across all the industrial type of systems out there. So to answer this need, the DDS sort of group came up with the DDS security specification, which I can't get into a lot of detail, but basically it addresses all those sort of needs and say, okay, how we're going to authenticate applications, how we're going to protect, provide access control, and more importantly, how are we going to do it at defined level? And that was the whole thing about perimeter defense, right? Now you're inside, but you imagine, like, let's take a hotel, right? So you may have somebody that at a hotel makes sure that when you come in, you're kind of like a guest and you don't have, may even like check you for weapons or something, whatever, but you're inside the hotel. That gives you like the right to come into the lobby and come into the thing, but doesn't give you the right to get into every room, right? So they have essentially a fine-grained access control where a person is actually given a key to take the elevator to a certain floor and then into a specific room. And there are several keys there, right? You get the same key as everybody can have a room in the same floor, because everybody can go to the same floor with that key. But even when you are in that floor, there's still separation so that you are only allowed to go into your own room. On the other hand, there are people, maybe like the service personnel that clean the room, that maybe have keys that open all the rooms or open sectors of the room. So you realize that it's very important to have this kind of granular access to the information control. It's not an all or nothing. And that's another thing that the DDS does when you tie it back to the information model, services, topics, these types of things. You can then say, okay, I want to give you permission, so you can be, you are a pump in this factory, and you are putting out there the pressure of this device. Well, that's the only thing that you can do, right? If you try to publish any other information, you're not going to be allowed to do that because you've only been given permission to publish that pump information, right? And this is really, I think, is subtle and is often missed in my experience, is one of the biggest vulnerabilities that are out there, because people are not so, they think security is kind of an on-off switch. Oh, I've got security, I'm done, right? But how many people have heard of that Jeep attack where people were able to take a Jeep that was riding down the road and essentially get it to turn it off the road and essentially make it crash, right? How many people have heard of that thing? How many people know how that was done? Okay, so that was kind of one of these elevation of privilege attacks. It turns out that the Jeep has a Bluetooth sensor in the wheel that communicates with the car whether the tire is inflated properly or not. So it can alert you and say, hey, your tire is low in air, right? So you've got a sensor in the tire that is supposed to just publish low air, high air, right? But the only permission that it had was not to publish low air, high air. It had permission to publish data on the bus. So somebody hacked into the Bluetooth device, some vulnerability in that stack, whatever it is, and now they had free range to put anything they wanted on the bus. So they started saying, okay, steer to the left, steer to the right, hit the brakes. All these things are signals on the bus, and this one thing that is only supposed to be saying, I have air or I don't have air, is now controlling your car, right? So this is the problem with granularity of information. You need to be able to give permissions just to the piece of information that you have and no more, right? And that's sort of a unique aspect of this DDS security specification, that because it has a very nice information model we looked around before, where you can say units and this and all these different things, you can also attach permissions very narrowly and only give permissions to the exact thing that you can do. So I mean, get into the details, but it also has capability to do plugin development. So we found that in different segments and sectors, people have very different needs for what kind of security, how do they authenticate applications, what kind of cryptographic techniques they want to use. So we couldn't come up with a solution that would work for everyone. So instead of trying to do that, we sort of built a plugin sort of interface that's a standard, so that somebody in the healthcare or somebody in the automotive can say, okay, I'm going to create my own plugins for authentication or for encryption, and plug them in and substitute what's out of the box available with the DDS with my own that does better encryption or better authentication or what have you. So finally, I already mentioned this is about essentially the granular control of access to the information, and also being able to monitor both the health, the availability. A lot of times, preventing modification of the information is just as important or more important than protecting the confidentiality of the information. A lot of times it happens in industrial systems. You actually don't care if somebody watches what you are saying. You don't want somebody to replace what you are saying, right? It's okay that people say, what is the current power, that is being generated, or even what is the current flight plan. In fact, they're being published on the web now with a little bit of delay, and you can see where all the flights are going. But you don't want somebody to be telling the flight to go somewhere else. That would be bad, right? So you don't care somebody to observe what's happening, but you don't want people to change what's happening. And that's done through another cryptographic technique, which is called message authentication codes, where you actually don't encrypt the data, but you kind of hash the content, and you kind of sign it in a unique way with a key, and then the receiver can validate that that message hasn't been touched, even though the message is still in the clear. And that's a lot cheaper than actually encrypting and decrypting. So in industrial systems that are real-time, that typically is something they do. And with DDS, you kind of select, do I want to encrypt? Do I want to just authenticate? Do I want to do this? Do I want to do that? On sort of on a very fine grain. So just to conclude, so why DDS? In industrial systems, there are very kind of stringent demands for scalability, for performance, for security, being standards-based. All these are important. And DDS has been around for a while. It's proven. It fits well the kinds of systems out there. And we actually find it as being sort of kind of a wave of adoption, right? As people are discovering this, they are discovering kind of this is the right way to do things. And in fact, we've developed sort of a set of questions to kind of classify people and say, well, are you a good candidate for this type of solution, right? I mean, what kind of things worry you about when it comes down to the low level of information exchange and communications? Do you care about reliability? I mean, do you have a consequence if your information is not available in a few seconds, right? Or is it okay? If you really care about that availability, continuous availability of information, you kind of check that box. Your unit of time because everybody is real time these days, right? But is real time to you milliseconds, or is it minutes, or is it hours, right? So if you think milliseconds, then check that box, or lower than milliseconds, right? And are you trying to build just a single system or a very large system with different teams across different kind of manufacturers and devices? You check that box. Is your data going from one point to another? I mean, are you just trying to aggregate everything into one place and that's it? Or are you having this kind of horizontal communication and vertical communication that we were talking about? You check another box, right? And then are you building sort of a system that is next generation is going to have to evolve over time? You check that other box. And if you get like sort of 3 of those boxes or more, then you need to consider this kind of technology, right?
Okay, thank you, Gerardo.
Right, thank you.